Hi, everybody. I hope you had a great weekend. We're wrapping up static electricity and moving into circuits now. And I'm going to show you this photo, even though my daughter will probably shoot me for it. This was quite a few years ago, and my daughter Katie, who's in this picture, and I were walking on a very remote section of the Great Wall north of Beijing. Now, it was a summer day, it was real humid, and her hair started standing up like this. Her face at this point, she's like, "Dad, why are you taking my picture?" And I'm like, "I'll tell you later. Just keep walking really fast." What was going on? In this case, it wasn't static electricity rubbing because of her shoes rubbing against the ground. It was an induced charge from the clouds. There was a thunderstorm nearby. No lightning yet, no thunder. But what I knew was happening was this. Let's say the bottom of the cloud became very positive, and the stick figure represents Katie, my daughter. What was going on? It was inducing electrons to flow up from the ground to her and up to her hair. So all of her hair became very negatively charged, along with her head as well. And so it started repelling. And this is the same kind of effect you may have seen before if you ever put your hand on top of a Van de Graaff generator, where it picks up a large charge. Why did I tell her I wouldn't explain what was happening? Typically, if this ever happens to you, you have seconds before lightning is about to strike that area. In this case, we're up on the top of this tall wall with no way to get off except cliffs on both sides and no exit points for kilometers. And so in this case, I'm like, well, I guess I should take this picture in case we do survive. Luckily, lightning never struck, but we were very lucky. And I want to go in a little bit more and just talk about static electricity. This app is linked to your assignment sheet. It's another PhET simulation. This is John Voltage, sorry. And let me just quick explain what happens here. You've got his finger here, and as you rub his shoe back and forth against carpeting, the shoe, which has a rubber bottom, is going to gain charge, and then eventually that charge, when it gets large enough, will literally, well, there it goes, will jump from his finger because all these negative charges here are repelling each other. They want to get away, but they've got to have enough potential, enough pressure to jump through the air from the fingertip to the doorknob. Now, what happens if I move his finger closer to the doorknob? You'll discover that it doesn't take nearly as much charge to jump across that very short distance. It takes a smaller pressure. The idea of pressure in electricity is represented by the concept called electrical potential or voltage. Now, you've all heard voltage before. For example, a standard 1.5 or AA battery is 1.5 volts. You've heard of 9-volt batteries, and most of you know that the plugs in Shanghai are at 220 volts. Or if you're in Japan or Korea or the US, they're at 120 volts. But what happens here if I move his finger very far away? Well, now I can charge up John Voltage as much as I want here, and I can't generate enough pressure for it to jump all the way from his body over to the doorknob. It's about as much charge as I can get on him. It doesn't have enough pressure to jump through the air, which is an insulator, all the way over here, unless I start moving his hand closer, at which point it does jump across. The idea of electrical potential or voltage is related to the idea of electrical pressure. How the greater the pressure, the further it can jump across this air gap. Let me head back to the PowerPoint. So here's our transition. We're moving from static electricity, which deals with stationary charges that only flow briefly as the charges or discharges. Like, for example, when I rubbed the PVC pipe against Fluffy, or if you take a balloon and rub it against your hair, or even John Voltage, it's only briefly going. Current electricity deals with a constant flow of charge. Current electricity required a more modern development That is a constant pump of charge. And you might say, what's this thing that constantly makes charge flow? And the answer is, it's a battery is what that discovery required. Just again, quick reminders beforehand, charge can never be created or destroyed. It simply moves from place to place, and most of the time that's electrons. Except in chemical reactions, sometimes you can have protons, H plus ions moving around, or other larger ions. Balloon on hair, yep, we already talked about the balloon steals electrons from the hair and becomes negative. What charge does your hair end up with? Positive, a deficit of electrons. The amount of charge on the electron is equal and opposite to the sign of the charge on the proton. But because we usually deal with large groups of these, we don't work with individual charges. We work with groups of them called a coulomb. Just like moles in chemistry, a coulomb is a convenient unit of charge. And now some definitions. Current, or first of all, charge, represented with the variable Q, and it's represented in coulombs, which abbreviate or is abbreviated with capital C. Our new topic today is electric potential. Or sorry, electric current. It's represented with the variable I. And it's defined as this. Electric current is how much charge, Q, flows through a certain point in the circuit per unit time. So you can write it as delta Q over delta T. It's measured in coulombs per second, but because it's used so frequently in everyday life, it's given its own special unit, which is the ampere, which ironically can be abbreviated two different ways, either the amp or capital A. So you might have something like this. You might say the current in a circuit is 5 amps. What does that mean? It means that there are 5 coulombs of charge per second flowing through the circuit at any given point. Electrical potential, and sometimes it's just called voltage, its variable is capital V, logically enough, especially if it's voltage. And it's defined as the amount of work done per unit charge. By the way, these couple of things, along with something called resistance, which we'll talk about later, are the big ideas in this whole unit. It's defined as the amount of work done per charge, so its units are joules per coulomb, work done per unit charge. But again, because it's useful frequently, it's given its own unit called the volt, or abbreviated V. Now, here is my mea culpa, my apologies, because if I could rewrite physics, this is one of the things I would rewrite. Why? You can now have equations that look like this. The electric potential in a circuit, capital V, is equal to 12 volts. That's an equal sign. There we go. Now you can, where volts is the unit of electrical potential. But what's the abbreviation for volts? Well, capital V. So what you've got here is the electrical potential is equal to 12 volts. And you're like, how do you tell the difference? Well, technically the variable should be bold, and the unit should not be. But if you look at this, you have V equals 12V, you're like, oh, V's got to be 0. That's the only way you can solve this algebraically. But here it is, my apology. The variable we use for electric potential is capital V, and the abbreviation for the unit of electrical potential is also capital V, but not bold. I'll try to make sure I don't confuse you at any point. The equation for it just looks like this. The electric potential V is equal to the potential energy of the potential energy it has per unit charge. So for example, if we say that a charge has a potential of 220 volts, that means each coulomb of charge has 220 joules of energy for each coulomb. That's a lot, which means, for example, if you want to warm up water and you want to put 220 joules of heat into it using an electric heater, you're going to have to let 1 coulomb of charge flow out of the outlet through the heater to release that much energy, because that's how much energy it has per coulomb. Now, the other mea culpa in this chapter. Ben Franklin Great guy. Invented libraries, fire service, a whole bunch of other things. Worked with electricity. We discovered that lightning was electricity, but he made one major mistake. What did he believe? He believed that it was positive charges that were free to move in the circuit. It was an educated guess. So what he thought was, if you have something that's charged positive and something that was charged negatively, and you connected them together with a wire, what would happen? Well, charge would flow from excuse me, my pen's lagging here, would flow from the positive thing to the negative thing. So if you hook this together with a wire, what would happen? Positive charge would flow from the one object to the other. And so he just said, this is the direction that current flows. It wasn't for another 100 years that the electron was discovered. But by then, people are like, well, we've always written current going from positive to negative. I guess we'll just stay with Ben Franklin's way. It turns out it doesn't change the magnitude, it just changed the direction. Yes, we now know that electrons are the object that actually moves around the circuit, but most of the time we still use Ben's definition for the flow. In fact, all of the circuits on the AP Physics 1 exam talk about conventional current. And you're like, what's conventional? Conventional is another way of saying old-fashioned, a la Ben Franklin definition of current. So what does it mean? If you've got a circuit here's a light bulb, here's a battery, we will define current as flowing from the positive terminal of the battery to the negative. Even though in reality what's really happening, the negative terminal of the battery has an excess of negative charge, and electrons are actually flowing this way through the light bulb and back this way to the circuit. But we'll always define current as going from positive to negative. You're like, why didn't they just change all the books? Well, at that point, it was 100 years in. It would have been confusing to try to change all the books. Imagine going through a library and saying, oh yeah, we need to change that book, we need to update this book. Oh, that book's out of print. Oh, doggone it, we'll have to just manually write in it. At that point, they just said, forget it, we'll just go with Ben Franklin's definition. Yeah, there's the real current. In reality, though, current electrons just don't move nicely through the wire. They really bounce more like balls in a pinball machine. An electron's average velocity in a circuit's called the drift velocity. And for most common circuits, like even in your laptop, the electrons are only moving a few millimeters per second. Now, some of you are like, whoa, wait a second. Yeah, even, for example, in your room right now, the wires or the electrons in the wires are only moving at about 2 to 3 millimeters per second. You're like, no, Mr. Clommer, you're lying to us. Why? Because most of you know that when you throw the little switch to turn on your lights, here's your lamp at the top of your room, that's probably 10 meters away. You're like, no, Mr. Clommer, when I turn on the switch here, it doesn't take 20 seconds for the electrons to get over here to turn on the light bulb. It would be really bizarre if it did. This can't be right, Mr. Clommer. It can't take that long for the electrons to make it up here. And the answer is you're absolutely right. What's really going on here is your wires are already filled with electrons, all basically at rest. What happens when you turn on the circuit? You start pushing the electrons. And the moment you start moving the electrons over on this side, moving the electrons over here, it repels the other electrons, and that repulsion moves down the wire at a rate you probably know already. The repulsion, the force, moves along the wire at the speed of light. C, for those of you who know the constant. Which means that normally most people say, how fast does electricity move? And you can simply say it moves at the speed of light, even though the electrons themselves are only moving at millimeters per second. Another analogy is if you had a bunch of people standing right next to each other, front to back, front to back, front to back, and you push the first person really hard, that push moves down the line much faster than the people move. And moving back around here. Ding, 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 ding. So, batteries do work on charge. They do not create or store charge. Just like a water pump doesn't make water. In fact, the analogy between batteries and water pumps are really quite good. A 1.5 volt battery does 1.5 joules of work on every coulomb of charge that passes through it. A 9 volt battery does 9 joules of work on every coulomb of charge that passes through it. What's the difference between these two? You can think about it as this is being a pump that is of higher pressure than this pump. This one generates a greater electrical potential, a greater pressure than this battery does. It does more work per unit charge. How do you make a battery? It was first discovered by Luigi Galvani. Sorry, just love a good Italian name. When he discovered that the nerves of the frog that Galvani's wife was preparing for soup, well, okay, first of all, I should explain it. I think his wife deserves the credit for this discovery, for discovering the electric battery. She was cleaning off frog legs in the kitchen to make soup that night, and discovered that while she was holding down, she was cleaning off, the nasty parts. While she was holding down the leg with a copper fork, she was using an iron knife to clean off the top of it. And when the iron knife touched the nerve, the frog's leg would twitch, even though the frog leg was, the frog was dead. And they discovered, wait a second, it happened whenever two different metals touch. Here's an image in Galvani's original book. Yes, I realize it's really disgusting. You take one piece of metal here and touch it to one side of the frog leg, another piece of metal over here to the nerve endings, and when these two pieces of metal touch, the leg will literally contract. And yes, he tried it with chicken legs, duck legs. It works with just about everything. Here he's doing it with, I think, a dog. Yes, it's gruesome. It's disgusting. In fact, it became the basis of Mary Shelley's Frankenstein, where they use electricity to sort of reanimate dead things. But the discovery here was this. All you need to make a battery or a cell is you have to put two dissimilar metals together. That's all it takes to make a cell. Now, quick note on this one. A group of cells together is called a battery. And so typically, unfortunately, a cell is just two pieces of metal, dissimilar metals. And if you've got a bunch of them in series, it's called a battery. But we tend to use battery for both of these. So here it is. Alexandre Volta built the first voltaic pile. This was the first battery. In it, I don't know if you can see it, he had pieces of copper, zinc, copper, zinc, copper, and zinc, separated by small pieces of fabric and then soaked in salt water. And if you took this thing here and brought it over to the bottom here, it would literally arc through the air. Why? This thing would generate hundreds of volts of pressure. And so it could literally jump from the bottom over to here without a problem. It was the first battery that produced a reliable, steady current and allowed some discoveries in electricity. I got to mention potatoes. If you haven't already done this, you may have worked with a potato before where you stick in like a nail on one side, which is coated with zinc, and a piece of copper, like a chunk of copper pipe, and you can actually light up an LED or run a clock with it. Here's the big idea. Is it the potato making the power, like it says here, potato power? The answer is absolutely not. What's really happening here is the fact you've got two dissimilar metals. It would light up the LED just as well if you replace the potato with an apple, with salt water, with lemon, weak solution of hydrochloric acid, a solution of sodium hydroxide, or even if you just put a person with sweaty palms who held both of those. The voltage is due to the difference in the electron affinities of the two metals you use. That's it. That's all it takes. So what's going on here? Here's a table of electron affinities. Some materials would love to gain an electron. For example, here, fluorine, chlorine, bromine, iodine, adenine. And some other materials would love to lose them, like over here. The ones in grays are kind of neutral. But what you end up with this is something interesting. Metals with greater difference in electron affinities produce larger electric potentials, do more work in the charge, produce higher voltages. Why am I bringing this up? Your computer right now, or your phone, use lithium-ion batteries. And you're like, okay, so lithium is definitely on this side, but what in the world is the ion that goes with it? Well, it turns out the ion is the H minus ion. And you're like, H minus? Yeah, remember hydrogen 1s1? It would love to have a full outer shell. So if it gains one electron, it ends up over on this side of the table. And so you end up with, it's got 2 electrons, but now it's an H minus. And it now falls into this column over, or nearby over here. I shouldn't have put it there. But now you've got 2 very dissimilar electron affinities and a fairly large voltage. It can store lots of energy. Talking about batteries, though, cells can be connected in series, that's one after another, or side by side, which is parallel. What happens if you do that? So, for example, here's some AA batteries. The little tip point here is the positive end. Most of you know that, and this is the other end. Here's where series, where the positive end goes back over here to the negative end, which goes to the positive end, negative end, which goes over here. And this device is a voltmeter. A voltmeter measures voltage or electrical potential. And so the question is, what will this meter read if you hook them up this way? Now, each battery here is 1.5 volts, or produces 1.5 volts of electrical potential, or does 1.5 joules of work on every coulomb of charge that passes through it. And the answer is, if you put them in series, it ends up being 4.5 volts. What happens if you put them in parallel? Now all of the negative terminals are connected together, all the positive terminals are connected together. What does the voltmeter read? What's the electrical potential in this case? And the answer is it's 1.5 volts, the same as the voltage of any one of the cells. And you might say, whoa, wait a second, what's going on here? Well, remember I told you that batteries are just like electrical pumps, and I did mean that in a real way. What's going on here? Having these one after another is like having a water pump where you pump water in, and then it comes out at higher pressure, which you then pump up a distance to another pump, which then puts it up into a higher pressure, which goes to another one, goes up to even higher pressure. Each one of these is increasing the electrical potential by 1.5 volts. What happens when you've got them parallel? It sort of looks like this. It's like taking water here at low pressure, and then it can run through any one of these 3 pumps up here. What happens in this case? It increases the maximum flow rate, but it doesn't increase the pressure. It's the pressure up here is the same as the pressure of one of these pumps. What happens over here? It increases the pressure, but not the maximum flow rate. The water still has to flow through each one of these, and whatever the flow rate is for one of these, that's the maximum flow rate. Whereas here, the maximum flow rate coming out here is 3 times the flow rate of any one of these, or could potentially be that much. Ooh, we're to a brain break. The famous foursomes below had all of their vowels removed from their names, and that had all the remaining letters squashed together. Can you figure out who and what they are? Okay, I got one. This one, number 4, north. I thought I had it. I thought that was west. Oh, it is. North, south, east, EA only allows the ST. North, south, east, and west is that one. Give it a try for the other ones. I'll again pause the video. You probably need a brain break right about now. And I'll give you a countdown, then I'll show you the answers. In 5, 4, 3, 2, 1, go. Ooh, Matthew, Mark, Luke, and John. That was a tough one. Oh, spring, summer, fall, and winter. Spades, hearts, diamonds, and clubs. Single, double, triple, and Homer. Oh, Homer! Earth, water, fire, and air. All those R's got me. I could not figure that one out. All right. How do you produce electricity? We've talked about batteries already. There's other ways to produce it as well. Magnetically, if you take a coil of wire and run a magnet through there, you can produce electricity. Piezoelectric, if you strike a crystal, like a quartz crystal, it actually produces an electric potential. Thermally, you can boil electrons off a heated metal. You can use a thermocouple, 2 different metals joined together and heated. Photoelectric really doesn't fall under thermally, but light photons kick out electrons from a material. And then nuclear ionization also doesn't quite fit underneath that. In nuclear reactions, you can have beta particles flying off, or alpha particles. Those are charged particles, and since they're in motion, you can transfer charge from one point to another. Now, gotta quick mention this one. Direct current versus alternating current. Batteries only produce direct current. That direct current means that current flows only in one direction. But the plugs in your room actually use alternating current. That's where the direction of the current actually flows or changes on a regular basis. In reality, what's it doing? It's actually doing, my pen's lagging again. It's actually doing this in a it's really bad. It's actually doing a sinusoidal function where the potential is varying with time. And if you hook up a light bulb or anything else to the circuit, the current will also vary with time. And what's the frequency of this oscillation? It is 50 hertz if you're in China. If you're in the US or Japan, it's 60 hertz, 60 times per second. In this unit, we're only going to focus on direct current, and the AP Physics 1 exam only also focuses on direct current and electrostatics. So we don't need to know alternating current, but I wanted to mention it because it's actually very, very common. If you look at your power adapter that you plug in for your phone, it says its input's usually like 100 to 240 volts AC, talking about alternating current. Batteries increase the energy of the charge that passes through it. When you complete a circuit, in other words, circuit means circle, you connect a wire from one end of the battery to the other side to complete the circuit. Charge loses this extra energy as it flows through the circuit and back to the battery. All circuits offer some resistance to the flow of charge. Resistance is like the opposition to the flow of charge. Resistance, the variable used to represent resistance is capital R, and it's measured in ohms. Now, and this symbol we used, or the abbreviation we use for ohms, is capital omega. And you might say, well, wait a second, why don't we use just capital O? Yeah, you could do that, but it would actually be really confusing. Say, for example, the resistance is 120 ohms, and you tried to use capital O as your abbreviation for ohms. It would get very confusing really quick. So instead, we do resistance is equal to 120 capital omega ohms. I got to give you this quick silly story. It's rather embarrassing. When I took physics in high school, we never got to electric circuits. So we never got to electric resistance. But of course, being the kind of nerdy student I was in high school, I of course read the other chapters. But when I got to this word in the text, there wasn't any pronunciation guide, nor had I heard it out loud. So I of course read it O-H-M-S, ohms, of course is the way it's pronounced. And so for the rest of my junior year, I thought resistance was an ohms. Throughout senior year, whenever I read a chart or a book, I'd always thought ohms in my head. And life went on. And then at university, freshman year, I was appointed as the physics lab assistant. Pretty cool for a freshman. I thought I was cool. And everything was going great. Professors would ask me to set up their labs. I'd set them up. They're like, oh, this is perfect. Until second semester, January of my freshman year. The professor walks in and says, hey, I need you to set up these electric circuits for the rest of the students. Just take this battery, this resistor, and make sure you use the 10 ohm resistor in the circuit, at which point I immediately interrupted the professor and said, no, you mean the 10 ohm resistor. He gave me a strange look and said, no, 10 ohms. And I without thinking, said, no, 10 ohm. And at that point, I went, oh, my goodness. For the last 3 years, I've been thinking about this wrong. Uber embarrassed. I went, oh yeah, 10 ohms. Yeah, ohms. Yeah, that's what I meant to say. So yes, I discovered how to pronounce that properly only after embarrassing myself tremendously. So resistance is measured in ohms. Moving on. How do you calculate the resistance of an object? Well, the resistance of an object depends on its material and the length and the cross-sectional area, how big it is across this way right here. Now, we represent this little thing right here is the Greek letter rho, and it represents the resistivity, and every single material has a unique resistivity. You're like, oh no, oh no, oh no, do I need to memorize these? The answer is no. How do you find these? You simply look them up in the Handbook of Physics and Chemistry, or your textbook, or Google it. Each material has its own resistivity. So the idea here is what causes greater resistance? Well, the longer the material is, the greater the resistance, and the bigger the cross-sectional area, the smaller the resistance. And you might say, how am I going to remember this? Well, think about it this way. If you had to empty, or let's put it this way, if you had to fill a swimming pool, if you just used one pipe, it might take a long time to fill the pool. But on the other hand, if you put pipes next to each other, in other words, increase the area that the water is flowing through here to fill your pool, you get a much larger flow, and your pool will fill faster. On the other hand, what happens if you try to put a very long pipe on here? In other words, say, for example, you had one garden hose, but now you decide, I can't reach the faucet, so you're going to put two garden hoses, one after another. Well, the longer you make the hose, the more resistance to the flow you have. If you haven't tried this already, if you ever try to put soda straws together and try to drink a drink, it gets more and more difficult as you add more straws in series, one after another. There's a greater resistance to the flow. So the other thing I got to mention about this is that calculating the resistance is not too bad with this equation, but in reality, resistance also varies a bit with temperature. For most materials, it increases with temperature. So as you heat up most metals, the resistance increases. For semiconductors, like silicon, the resistance actually decreases with temperature. There becomes more free electrons as you warm up semiconductors, which causes some problems. I guess I should mention real quick. Early computers used to have this terrible problem of the CPU bursting into flames. You're like, what? What's going on? Well, think about it. Most of you know your laptop gets crazy hot while you're using it. That's all because of the CPU, the main processing unit, gets quite hot while it's running. You can hear the fan on mine running if you listen closely on this recording. The problem is, in the early computers, as resistance became smaller, it means it was easier for electricity to flow through the circuit, which meant more current flowed through the circuit, which then made it hotter, which meant that it was even easier for electricity to flow through, which meant more electricity to flow through it, which made it even hotter. It was called thermal runaway, and literally the chip would just get hotter, 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 and then go boom. It would literally explode, and a little smoke would come out of your computer. That was not cool. Nowadays, your computer's a little smarter. It has temperature sensors, and most of you know that your computer literally will slow down if the CPU gets too hot. Why? To protect itself from thermal runaway. The one other thing I want to mention here real quick is, for most metals, something very strange happens. If you get them cold enough, suddenly the resistance will drop to zero. What's happening at that point? At this point, it becomes something with zero resistance. It becomes superconducting. And all metals have a critical temperature. Most of the time, it's only a few degrees above absolute zero, 4, 5, 6 Kelvin. And at that point, it becomes a superconductor. Above that point, it has some resistance. Here's the resistivities of a bunch of materials. So you can see that materials with the greater resistivities are going to have this larger resistance given the same length and area. On here, take a quick look. Which is the best conductor? In other words, which has the smallest resistivity? And you're like, oh, duh, it's gold. Not really. Take another look. The best conductor is actually silver. And you might say, well, wait a second then. Why don't we use silver more in computer circuits? For example, if you look at your headphone jack, if you still have it, or your USB connector, the better ones are always coated with gold. Why? Because gold's a pretty good conductor. Not as good as copper, by the way. It's like the third on the list here. But why do we tend to coat things with gold if we want better electrical conductivity? And the answer is, if you haven't already figured it out, is gold doesn't form oxides or chlorides or sulfates, whereas copper and silver do. And so even though pure silver and pure copper are better conductors than gold, in reality, when copper and silver are exposed to air, they tend to oxidize, or in copper's case, or silver's case, tends to create sulfates. And those salts don't produce, or are not electrical conductors. So we tend to coat things with gold, and it's not the best conductor, but we don't have to worry about it oxidizing. So here's a quick conceptual question using the idea of resistivity. Which one of these would have the greatest resistance? Which one would have the least resistance? And hopefully you would recognize, all right, the longer they are, the greater the resistance, and the smaller the cross-sectional area, the greater the resistance. Which one has the most resistance? You should say, oh yeah, this one here. So B has the most resistance, followed by, trick question. This one has half the length and half the area, then this one is greater than A equals C. Both of those have the same resistance, and they're the least. Here's a quick plug and chug problem. I want to show you how this works. A 1 millimeter diameter copper wire is 100 meters long. What's its resistance if the resistivity of copper is that from the table? All you do here at this point is simply plug and chug. You plug in the resistivity, you plug in the length, and then you plug in the cross-sectional area, which in this case is pi r squared. The only trick on this one is you've got to remember that 1 millimeter up on top here is the diameter, so the radius is going to be 1/2 of that, so 1/2 of a millimeter, and you get 2.12 ohms to 3 sig figs. Now I talked about the fact that most materials heat, or as you heat them up, the resistance increases. You can use either one of these two equations, where you can either modify the resistivity based upon the change in temperature, or you can take the original resistance and figure out the new resistance if you know the change in temperature. Where alpha here is called the temperature coefficient of resistivity. Where do you find that? Again, in your handy-dandy Handbook of Physics and Chemistry, or Google it, or use the table in your book. Here's a table from another book, and you can see here, you can see the resistivities over on this side, and you can see temperature coefficient over here. Here's the alpha. This is rho, even though it's not labeled as rho in this table. By the way, notice the resistivity of some other materials here. Glass is a pretty good insulator. It has a very large resistance to the flow of charge. Rubber, sulfur, fused quartz are all these kind of things. And all these values are at 20 degrees Celsius. That's where these temperature coefficients and resistivities are coming in. So here's a quick example. A carbon resistor has a resistance of 100 ohms at 20 degrees Celsius. What will be its resistance if we warm it up to that temperature? How do you solve it? I'm going to use this equation down here because I know what the original resistance is already. It's 100 ohms. So 100 ohms times 1 plus alpha times the change in temperature, 100 minus 20 or 80. In this case, carbon is actually a semiconductor. It actually becomes a better conductor as it warms up. And so in this case, when you plug it in, you'll discover that your 100 ohm resistor becomes just a 96 ohm resistor if you warm it up to this temperature. Ooh, holy cow, another brain break. The names of several countries in Europe are 6 letters long. Given one letter in a set position, fit them into the grid below. When you're finished, read down the shaded column to spell out the capital of one of these. Monaco. I think this one might be Monaco. That's the one that's an easy one because it starts with M. The rest of them, not Denmark. Denmark won't work. That's 7. I'll let you work on this. I'm going to do a quick countdown. Take a break. Pause. Take a break from physics and the math for a second. See if you can figure out the other ones. I'll see if I'm right with Monaco. In 5, 4, 3, 2, 1. Okay, so it was Monaco. Sweden up. Serbia. Serbia is still a country. Cyprus, Poland, and Norway. And it does actually spell the capital of Poland, which is Warsaw. Fun. All right. So quick review here. And I keep using plumbing analogies, and it is actually really, really good. Charge in coulombs is just like volume, water volume measured in cubic meters. Current, measured in coulombs per second or amperes, is just like flow rate in cubic meters per second. Potential in joules per coulomb or volts is exactly equal, if we follow these same methods, to joules per cubic meter or newtons per meter squared. Turns out they're exactly equal to each other. So divide both sides by meters, you'll end up with that, or pascals. And so electrical potential is exactly like pressure on this one. And resistance is like flow resistance in a plumbing circuit. Unfortunately, plumbers don't have an analogy for ohms. They just call it flow resistance. And it's the big idea on this one. So, circuit schematics. So instead of drawing out batteries all the time, we tend to draw them out using symbols. So the symbol for a battery are two parallel lines, one of which is longer than the other. Why? These represent the two metals that you put together to form a battery with some sort of solution or a potato in between if you want. The longer one is always the one that loses electrons and becomes positive. The short one's the one that gains electrons and becomes negative. It has the greater electron affinity. So this is the symbol for a battery. And let's say this is a 6-volt battery. And then this is the symbol for a resistor. And I always think about, it looks like a rough road. Nink, 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 nink. And it's difficult to drive down. You're driving down the road, it's all smooth. All of a sudden you run into the bumps, it slows you down. And again, remember, it's measured in ohms, which we can abbreviate with omega. If charge is positive, which way does current flow around the circuit? The answer is we define current as the direction that positive charge flows. And so we would define current as flowing around the circuit in this direction. If I can draw my arrow here, sorry. Flowing around it in the anti-clockwise or counterclockwise direction. And in this case, we haven't talked about this yet, but the current would actually be 0.5 amps. So we'll talk about that in just a little bit here. The thing I got to mention just real quick is the symbol for a resistor. On the AP test, it's going to be drawn this way. In the US, resistors are always drawn this way. This is the schematic for a resistor. But in Commonwealth countries, resistors are simply drawn as little boxes like this. The software I use to draw circuits, and some of you might use it a little bit later this chapter, is called Yenka, and because it was written in the UK, it draws resistors this way. Please realize that whenever you see this symbol, like 2 ohms, please know that that's a resistor, even if it's not drawn with standard notation. So remember, voltage is the electrical equivalent of pressure, current is the electrical equivalent of flow, resistance is the opposition of the flow of charge, measured in ohms. Does a voltage always create a flow of charge? And now think about this in terms of water for a moment. Just because you have water pressure, do you necessarily have a flow of water? Think, for example, in your bathroom. The water in the pipes are under pressure, but is there a flow necessarily? The answer is no, not necessarily until you turn on the faucet or the tap. The same thing's true with electric circuits. I guess I should draw that. If you've got a battery, you do have electric pressure, but there's no flow in it until you complete the circuit. So in this case, if I have a resistor here, there's absolutely no flow until I complete the circuit. Now, the one difference in this case, if this was a water pipe and I just left it open here, water would flow through the air. But unless you've got a really crazy large pressure, normally electricity doesn't flow through air because air has a very large resistance. So the only time you get a flow is if you complete the circuit with a wire here, and now current flows around the circuit. Just like with water, even though you've got a pressure, there's no flow of water until you open up the tap and allow it to flow down the drain. This is George Simon Ohm, and he discovered that there's a nice relationship between these three quantities. The current in an electric circuit is directly related to the pressure, electrical potential, divided by the resistance in ohms. And that's why we name, or the unit for resistance is named after George Simon Ohm. Oh, there's a great story about him. Oh, never mind, I'll talk about it later. And some previous AP Physics 1 students, I said, I don't get this whole thing, this Ohm's Law thing, until I saw this cartoon one time. I was like, Mr. Conway, you got to share this cartoon with all future students. I'm like, okay, I got it. I'll do it. So in this case, resistance, measured in ohms, is trying to restrict the flow of people down this pipe, or in this case, I guess this represents electrons. And the flow of this is, of course, is the current measured in amps. What's pushing this all around? It's the pressure, the electric potential measured in volts. So how could you increase the current flow in a circuit? You could either reduce this restriction, reduce the resistance, or you could increase the pressure. What if you want to restrict the flow? Well, you could either increase the resistance and or decrease the pressure, the potential involved. So take a quick look at these circuits. In which of these circuits is the light bulb brightest? And you might say, whoa, wait a second. How do you, okay. So brightness of the bulb is directly related to current, which is just going to be V over R. Now remember what we talked about with batteries in series and parallel. In which of these cases is the light bulb going to be brightest? And the correct answer is, they're all the same. Why? The electrical potential in each one of these cases is 1.5 volts. The bulb has some resistance R. Here, when I've got two batteries, it's still 1.5 volts because they're in parallel. This is still R. Here, it's still 1.5 volts. The resistance is R. And the current is going to be the same in all of these. You might say, but wait a second. Didn't you tell me if you've got them in parallel, you could get a larger possible maximum current? Yeah, you could. But in this case, the resistance is the same. The current's going to be the same on all of these. The maximum potential current is larger in this one and this one than that one, but it won't affect the current in this circuit. What about this case? In this case, take a look at the batteries real quick. This one, of course, 1.5 volts. The resistance is R. Here they're in series, total of 3 volts, resistance of R. Here, take a look at it. Negative end connected to negative end. So this battery is trying to pump charge or run current this way. This one's trying to run current this way. And they're equally matched pumps. They both have a potential of 1.5 volts. What's going to be the voltage in this case? Some of you might recognize it's going to be 0 with the resistance of R. In this case, this one's pumping it this way. This one's also pumping it this way. And they're hooked in series. This is 3 volts. Whoops, that's supposed to be just 3. Oh, my poor pen. Which one's going to be the brightest? It's going to be a tie. B is equal to D. They're both 3 volts, which is greater than A, which is greater than C, which has no current at all, and the light bulb's not on at all. Now, using Ohm's law, we can actually calculate a few things. What's the current in this circuit? Well, if you use Ohm's law, I equals V over R. What's the current in this circuit? It's 1.5 volts over the resistance, 0.5 ohms. And the current in this circuit is going to be 3 amps. Which way is it going to flow? Well, we're going to use conventional current. And so we're going to say that 3 amps is flowing out of the battery in this direction, from the positive terminal towards the negative. Now, here's a tricky question. What's the current at this point in the circuit and the current at this point in the circuit? Well, believe it or not, it's still 3 amps. And you're like, whoa, wait a second, what's going on here? If we would change the current, that would means there's fewer number of coulombs per unit of seconds. In other words, I lost charge somewhere in the circuit. But remember, charge is never created or destroyed. So I can't actually lose current as I go around the circuit. If I did, it means I was losing charge somewhere. It was disappearing. So you might say, well, wait a second then. If the charge doesn't change, what's powering this light bulb over here? In reality, it's the change in the electric potential. There's a loss in energy as the electrons go through here. We don't destroy the electrons, but we do destroy some of its energy. Just real quick, I want to show you this. If you take Ohm's law and rearrange it, you can get V is equal to I times R. So what's the change in voltage as it goes through this light bulb? It's equal to the current times the resistance. So what's delta V for this light bulb? It's equal to 3 amps times 0.5, or the change in voltage is 1.5 volts. So what's happening here? And this is where I'm going to leave you for tonight, and you should be in good shape, is what's happening in the circuit? Well, let's say I define the electrical potential at this point in the circuit to be 0 volts. What happens after it goes to the battery? It gains 1.5 volts of potential. And that stays the same even right before the light bulb. It's still 1.5 volts of potential. But then when it goes to the light bulb, it's going to lose that much. What's the potential over here in the circuit? It's now down to 0 volts. And here it's 0 volts. And it returns as 0 volts, gets pumped back up to this. It loses all of that in the light bulb, all the electric potential, all the energy it gained going for the battery, and then returns until it gets pumped back again. You might say, well, wait a second, does it have to use up all of it? Couldn't it come back here with like 0.5 and then beat 0.5, 0.5, then go for the battery and it becomes 2 volts, and now it loses just 1 volt of that and it comes 1 volt here? If you did that, you run into a runaway where the potential would just go towards infinity. So no, it does not happen. In a circuit, we lose all the potential that we gain from the battery every single time. With that, have a great night, good luck, and we'll talk to you very soon. Bye.